Theorem 9.8, the limit of the nth term of a convergent series. Okay, if the series does converge, levels off and approaches some sum, if it doesn't diverge to infinity. Okay, if that series does converge, then we know that the limit of the nth term is 0. And that's the only way that the sum can approach some leveling number, is that if the later terms are going to 0. Because think about what we're doing. We're adding them all together, and if your later terms get larger and larger, you're just adding a larger number to the previous sum. Well, it's not going to level off. So this is a true statement. If the series converges, then the limit of the nth term is equal to 0. All right. The converse of that statement. Okay, now, just because we know that the limit of the nth term is 0 doesn't necessarily mean that the series is going to converge. Okay, that's not generally true. So if the limit of the nth term is 0, then the series may either converge or diverge. So if I stop here and kind of make an analogy, think about this for just a second. Every square is a rectangle. So that's like saying that if we have a square, if the series converges, if we have a square, then we have a rectangle. So if a series converges, then the limit of the nth term must be 0. But think about the converse of that analogy. If we have a rectangle, it doesn't mean that we have a square. All right, now let's look at the contrapositive. If the limit of the nth term does not equal 0, it's some other number, then the series must diverge. So what we're going to be doing is we're going to be looking at nth terms. We're going to be looking at the series, the nth term of the series, and we're going to be looking to see if the limit doesn't equal 0. Because if it doesn't equal 0, then we do know that the series must diverge. Okay. And so that leads into this theorem, Theorem 9.9, the nth term test for divergence. If the limit does not equal 0, then the series diverges. So let's see what that looks like in some examples. So in the coming days, we're going to be looking at different tests on series to determine if those series converge or diverge. So our very first test, okay, is a test for divergence, not convergence, but divergence. So this test says that if the limit of the nth term does not equal 0, we know the series won't approach some leveling number. So let's look at this example for just a second. The series given by 2 to the n. Okay, well, let's maybe generate a few terms first of all, have an idea of what that looks like. So if n is 0, we start off with 1. If n is 1, we have 2. If n is 2, we have 2 squared, 2 cubed, etc. Plus some 2 to the nth term plus, and it keeps going. So if you think about calculating different partial sums, like s sub 1 would be 1, s sub 2 would be the sum of these two, or 3. The sum, the third partial sum, would be the sum of 1 and 2 and 4, which is 7. Add another 8 here, that's 15. If you keep adding, you're not leveling off. Okay, that sum is going to infinity. So this tells us that the series is going to diverge just by looking at what's happening. Okay. But for this test, the nth term test for divergence, the very first thing you might want to do is, to answer the question of convergence, divergence, is find the limit of the nth term. Meaning limit, as n goes to infinity, of 2 to the n. Okay, so we're used to finding limits. So what we do here is we plug in infinity for n, and we can quickly see that that number right there goes to infinity, and infinity does not equal 0. So we can say then, therefore, stack of 3 little dots here, there should be 3, okay, that by the nth term test, the series diverges. And it's always good to kind of say what test you're using. By the nth term test for divergence, the series diverges. Because you've shown that the limit of the nth term does not equal 0. Okay, before we move on, let's just reconsider this same example. You might have noticed that this is actually a geometric series. Okay, if you notice that it's a geometric series and the common ratio is more than 1, well, the geometric series says that if you have a common ratio more than 1, that series is going to diverge. So we can actually talk about convergence and divergence of this series in two ways. By the nth term test for divergence, okay, or that it's a geometric series with a common ratio greater than 1. So it's whatever you're comfortable with. If you want to go straight to finding the limit of the nth term, or if you quickly identify that as a geometric, you know, it just depends. I mean, you could have said it diverges because r is greater than 1, and that's certainly acceptable. All right, look at the second example right here. I mean, with all the factorials in it, okay, it's not geometric. So if it's not geometric, I don't know what the common ratio is. Well, there's not one because it's not geometric. So at this point, if I want to figure out if it converges or diverges, you know, we're really just left with one test right now. In the coming days, we'll have other tests to consider. Okay, but right now, we're just going to look at the nth term test for divergence. Okay, it might be helpful to expand, create a few terms from this series, just to get an idea of what those numbers are doing. All right, if n is equal to 1, that kicks us off here. Okay, everywhere I see n, I'm going to replace it with 1. So 1 factorial over 2 times 1 factorial plus 1. Okay, we'll simplify that in the next step. Let's just generate a few terms with the factorials in it. And if you don't remember what that is, I'll quickly remind you. Now let's let n be 2. So 2 factorial over 2 times 2 factorial plus 1, and that's a factorial. Then one more. And this could continue, plus dot 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 plus an expression for the nth term, which is just this expression right here, plus dot dot dot, just to indicate that it's a series. Okay, so let's come up down here and simplify this. So 1 factorial is just 1. You'll remember what it is in just a second. Okay, so look down here. 2 times 1, first of all. Okay, 1 factorial is just 1, so 2 times 1 is 2. 2 plus 1 is 3. So this right here is equivalent to 1/3. Let's move on here. 2 factorial means 2 times 1, so the numerator is 2. So factorial just means starting with that integer, multiply by every integer that's 1 less than it. So here in a minute, 3 factorial is equivalent to 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Okay, so coming back here, let's clean up the denominator. 2 factorial is 2. 2 times 2 is 4. 4 plus 1 is 5. All right, here, 3 factorial is 6. 3 factorial first, following the order of operations, is 6. 6 times 2 is 12, plus 1 is 13. I'm just trying to get a peek in at the value of these fractions to see if I can guess if it converges or diverges if I were to go back and add all these fractions. So we're going to have 24 on top. This is 24 times 2, 48 plus 1 is 49, and we could continue this pattern, plus dot dot dot. And I'm not going to take the time to rewrite this term here. So observing the values of each of these fractions, this is 1/3, 0.3, this is 2/5, 0.4. This right here, 6 over 13 is getting closer to 1/2. 24 over 49 is even closer to 1/2 than the previous one. So it appears that my terms are maybe increasing to 1/2. So if I were to go back and add all these together, but keep adding another 1/2 and another 1/2 and another 1/2, I think we can understand that the sum's not going to converge. All right. So, but that's not enough just to say that I think that, you know, the sum of the series is going to diverge. I need a test to prove its convergence or divergence, and that's where the limit of the nth term test, comes in. Okay, so at this point right here, we're going to say, well, the limit as n approaches infinity of n factorial over 2 times n factorial plus 1, once we find that limit, okay, we might have an understanding of what this series does. Okay, you may be familiar with the comparison of the degrees in determining if a rational function, you know, approaches a horizontal or a slant asymptote, and actually this is the same kind of situation. You know, think of this as a rational function. Okay, think of these factorials as kind of canceling each other out. So, you know, what are we left with when we look at what has the most impact on these terms? Well, n factorial does, and so does 2n factorial. The plus 1 is kind of insignificant. So when we look at this limit, think of the comparison of degrees of a rational function, and this kind of follows the same kind of rule. N factorial and n factorial cancel each other, so the limit is going to actually be 1/2. So it's kind of like an n behavior limit situation. Well, 1/2 doesn't equal 0, so these terms are approaching 1/2, and if I keep adding that, okay, I'm not going to converge. So we've shown the limit does not equal 0. So from that implies that this term or this series diverges. So you would just simply state by the nth term test for divergence, this series diverges. If it doesn't equal 0, it diverges. So that's a quick test to do at first if you're familiar with how to find these limits. Okay, taking a look at this last example right here. First thing I kind of try and look for is it geometric? And if it is, what's the common ratio? Because that's a quick understanding of if the series will diverge or converge. Well, it's not geometric. Okay. So let's just generate a few terms and see if we can get an idea of what happens here. So n is 1, we get 1. N is 2, it's 1/2, 1/3, 1/4, etc. Plus the nth term plus ... Okay, so peeking in at this, it really appears to me that these subsequent terms are getting smaller and smaller and smaller, and the value of each of them are probably approaching 0. So it's very possible that this series is going to converge. Okay, but right now it's not geometric, so we can't discuss convergence or divergence from that perspective. All we have to go on is finding the limit of the nth term. Okay, so what's this limit? Well, as n goes to infinity, as this value goes to infinity, the value of the fraction approaches 0. Okay, so this is 0, so think back up to the very beginning, the top of the notes, the converse of Theorem 9.8. Just because we know that the limit of the nth term goes to 0 doesn't give us any idea whether this series converges or diverges. So from this it follows or implies, that's what that symbol means, okay, that the nth term test does not apply. We don't know if it converges or diverges. So for the moment, we're going to have to leave this series, but in a later video, we're going to see a different test that will show us actually that this series is going to diverge. For divergence, oops, does not apply. So like I said, temporarily we'll have to leave this problem and we'll come back and revisit it when we learn more tests.